Well, traditionally, PP series have had always a chapter on meteorites and the constraints from meteorites on either formation of terrestrial planets, formation of solar system. So today we're going to have a chapter, a talk on meteorites given by Thomas Stephan. Thank you very much. I'll give you a sign after 30 minutes.
Good morning, everybody. First of all, I'd like to thank the organizers for inviting me to give this talk. Unfortunately, I was not able to attend the meeting so far. I arrived last night. So in the next 35 minutes, I'll try to summarize what has been learned since the last Protostars Planets conference from samples from the solar system. That would usually take like 2 or 3 hours, and since the organizers were not able to give me such a big time slot, so I picked some highlights, and here I would like to thank my co-authors for not being here so I could pick the highlights I thought would be the highlights. Okay, so quick outline of my talk. I will start with results from the Genesis mission. What have we learned from this sample return mission? I'll talk about volatile elements, about early solar system chronology, putting everything on a time scale. I will talk about pre-solar grains, what have we learned from these stardust grains, and then I will switch over to Stardust the mission, and a few words about the Hayabusa mission, and talk about new instrumentation and summarize. So the Genesis mission was really one of the highlights during the last couple of years. It was a launch in 2001, and the return to Earth took place in September of 2004. It was planned like this. They actually hired 2 stand pilots from Hollywood to capture this capsule slowly moving in on a parachute, pick it up so it would never touch the ground, to rescue these precious samples that sampled the solar wind, and you will see in a minute that it didn't go that way. But what was the purpose of Genesis? Genesis had all these collectors here to sample solar wind. This was put into an orbit around one of the Lagrange points, L1, and it collected solar wind for close to 30 months and brought this back to Earth. And then something happened. Here one picture of one of those collectors, very pure, very clean material, different kinds of materials for studying the elements and their abundances and the isotopic abundances in the solar wind. But then something happened what NASA in his official press statement calls a non-nominal re-entry. Well, the parachute didn't open because maybe one of the cheapest parts on the spacecraft, a little switch, was put in the wrong way, upside down. It was supposed to open the parachute. It didn't work. So there was no work for the stunt pilots of these 2 helicopters because there was no way to catch this capsule and prevent it from smashing into the ground. That picture actually doesn't look that awful because you would think, okay, it's just stuck into the ground. But the Utah desert is pretty hard. It's not stuck on the ground, it's on top of the ground, so the spacecraft here is basically flat. Okay, but it's still a great success. Because despite the non-nominal re-entry, the main scientific objectives of Genesis mission have been met. And there's nothing that cannot be measured in the future because of the crash. We still have the samples. Results have been slow to come out of Genesis, primarily because of the exceptional analytical challenges to analyze small numbers of atoms concentrated in regions only a few tenths of nanometers from the surface of the target. But after getting rid of all the dirt, all the Utah desert, we ended up with thousands of samples. And actually, there was only one thing that was pretty disappointed. Some people spent like half a year for developing a technique how to split these samples, how to cut them into little pieces in a very clean way. Well, in this case, it was done by the Utah desert. And we ended up with thousands of samples and a lot of science to do, and some cleaning procedures had been developed. And yeah, we could get all the science out of it, and we're still getting all the science out of it that it was planned for. One of the major purposes of Genesis was to measure oxygen. Although oxygen is pretty abundant in the sun, there was no clue what the oxygen isotopic ratio in the solar wind would be. And here you see basically the status before Genesis. So this is the world of oxygen isotopes in the solar system. I should explain to those of you who are not familiar with this notation. This is showing a 3-isotope plot with delta notation. Delta O18 means the deviation of the O18 over O16 ratio, the deviation from a standard. In this case, it's standard mean ocean water, basically the deviation from that standard, and the same here for the O17 isotope. So delta values are deviations from that value in per mil. This is where this factor of 1,000 comes into play. So the Earth and the Moon lie on this one. This is a line with a slope of a half. This is the so-called terrestrial fractionation line. It means that if you have a physical process that to some extent separates isotopes, it has a 2 times bigger effect on the O18 because the mass difference to O16 is by a factor of 2 bigger than for O17. So everything ends up usually on the line with a slope of 1/2. And there is this line for the Earth and the Moon, and there are different meteorite classes that typically form their own lines that are in parallel, but they are all very close to this line. But then there is this other line, this CCAM line. You can read here what this means. These are measurements obtained from very primitive samples, from meteorites, from so-called calcium aluminum-rich inclusions, or CAIs. These are the first solids that we think condensed in the solar nebula. So these are basically the oldest rocks in the solar system. And some of them tend to line on a different line, and this line has a slope of 1. Slope of 1 in this case means if you start somewhere here on this line, so where most of the solids of the solar system are, and if you would go down, this could happen by adding O16. There's no way with a normal mass-dependent fractionation to generate this, but by adding O16 you end up here on that line. So there were samples known on that line, and now the big question was, where would the sun be? Would the sun be where the Earth, the Moon, where Mars is, where the meteorites are, or would it be on that line? And we learned from Genesis, and I should first say that it was really luck that the specially designed sample for collecting the oxygen isotopes, that it was basically intact. 3/4 of this little sample here were really intact, and this was a special sample designed for collecting oxygen. Here it had a special electromagnetic or electric concentrator in front of it to enhance the oxygen abundance in that sample. So you can see here, Genesis showed us that the solar wind is somewhere down here on that line, and the previous plot was all in this upper corner. Actually, it's a little bit more complicated. Solar wind was found to be even here on this, but there are some calculations that show that there is some mass fractionation in the solar wind, that actually the sun is not here where this measurement, the raw data basically are, but it can be corrected. So the sun, as I said, is on this line where these CAIs lie, and not where Earth and Moon and the meteorites are. So that means, since the sun is a major mass in our solar system, that's the normal, and the Earth and the Moon are oxygen-16 depleted. If you look at old plots, you often see relative to sun, but most what people measured was relative to Earth. But the Earth is not normal. It's not the average composition of the solar system. It is down here. There's been a lot of progress in how to explain this. How does this happen? I want to briefly mention one model. That's the so-called CO self-shielding model. If you have a gas disk and you shine light on it, you dissociate CO into C and O atoms. But this is a very effective process, but it's kind of taking up all the photons with the right wavelengths in the first part of that cloud, and you basically shield further down in that cloud, you shield the process of the photodissociation of CO with O16 to happen, since for the other two processes with the much rarer oxygen isotopes, since you need slightly different wavelengths, this still happens deep into that nebula, into that protoplanetary disk or molecular cloud. So by this process, you can enrich free O17 and O18 that goes into water and might react with solids and change their isotopic ratios to O17 and O18 enriched isotopic ratios. So there's still some debate where this self-shielding takes place. I think this guy is not working very well. Okay, since there are different things discussed at the surface of the disk outside of 30 AU, at the edge of the disk close to the sun, in a pre-solar molecular cloud. So there's a lot of debate going on still where self-shielding takes place, or if this is at all the dominating process for the strange oxygen isotopic ratios that we find in the solar system. So one still must consider that there might be some galactical chemical evolution leading to differences between solids and gas to start with when the solar system formed. So if the solids were O17 and O18 enriched, then if you start with such a composition, you could also explain what we observe in the solar system. So I just want to show you that there's still some debate and it's not clear. Most people right now seem to prefer the self-shielding model, but I think this is also a valuable model, and this might be the cause for what we observe. Another isotope that was planned to be measured with the Genesis samples were the nitrogen isotopes. Here is basically shown the solar system in nitrogen isotopes. Nitrogen only has two isotopes, stable isotopes N15 and N14. So here's the N15 and N14 ratio, and here it's plotted over the D to H ratio. Here are the Earth and the meteorites and Mars. They are clustered in this area. Comets seem to be way out here at higher nitrogen 15 to 14 ratios. Jupiter is down here. And we, again, had no idea where the sun would be. There were some ideas, but only Genesis told us where it is. And this is where the sun is, basically exactly where Jupiter is. Of course, you could say there is no D2H, no deuterium in the sun. The sun destroys deuterium, so we plotted it here, where we think when the sun formed, where the initial value for D2H was. So again, nitrogen in the Earth is not normal. Nitrogen, it's N15 enriched in the Earth, and there again are models how to explain this. Way more complicated self-shielding model, and way more complicated that I would be able to explain this to you in a couple of minutes. Talking about D2H results, although this is not here from Genesis mission, but since I had this on the previous plot, I thought I should say a little bit about this, because there's always the question, where does the water on Earth comes from? Here there's also some progress being made. We have now some data from a number of comets during the last couple of years, and since they seem to have higher D2H ratios than we observe here on Earth, it seems to be very unlikely that the water, like it was proposed for many years, on the Earth is coming mainly from comets, because if the Earth would have acquired something like this, we would expect the Earth to be up here, because if the Earth subsequently would lose some of its hydrogen, it would always lead to some D2H enrichment. But since the Earth is on the lower edge of the comets, this doesn't explain, would be hard to explain with the water coming from comets. So the newest ideas are that it comes from very primitive meteorites, like Ci or Cm meteorites that are down here. And these are the new data that had been acquired during the last couple of years. So that seems to be making more sense, and that the water is coming from those meteorites, or that come from asteroids. Let's talk a little bit, let's switch a little bit gears, let's talk a little bit about solar system chronology. As you all know, time is a crucial parameter in constructing any story, and long-lived radionuclides, like the uranium isotopes, thorium, rhenium, lutetium, you can read the list here. They provide the basis for solar system chronology. They deliver us absolute ages, and when we study solid material from the solar system, like meteorites or rocks here on Earth. But beside those long-lived radionuclides, we have a number of short-lived radionuclides that also existed when the solar system formed, and they can be used to determine relative ages. Relative ages allows us to placing events in their proper sequence and measure the duration of events, and they usually give a much higher time resolution than these long-lived radionuclides. And this is the actual list. I think it's really up to date. Recently prepared this list that's showing all the short-lived radionuclides that we think that were alive when the solar system formed, and it goes even down to very, very short half-lives. So you have here the parent, the daughter, but you don't need to read all this. I think that will be in the chapter. Now, to tie the high-resolution relative ages to an absolute chronology, a correlation must be established between the short and the long-lived chronometers. The ratio of the extinct nuclide to its stable partner isotope must be established at some known time, and this time it's usually one picks something like the origin of the solar system, which from our point of view is usually the crystallization age of the first rocks formed in the solar system. I mentioned calcium aluminum-rich inclusions, for example, but it also often refers to some other well-defined fractionation effect, like fractionation of a planet or whatever. For reconciling relative and absolute chronologies, the aluminum 26, magnesium 26, and the lead system have been investigated in CAIs and chondrules. CAI and chondrules is what we find in these primitive meteorites called chondrites. Chondrules are these round objects, and chondrites are usually full of these chondrules. And there are these CAIs that I mentioned already several times. This is an image showing the concentration magnesium, calcium, aluminum in the three colors, red, green, and blue. And these CAIs seem to be the most primitive. These are high-temperature condensates, the most primitive, or the first condensates in the solar nebula. So if we want to learn something about this, it's nice to reconciling relative and absolute chronologies by matching these systems, and other systems have been used to study planetary melting effects and other things. But there's a big news in the uranium-lead system in dating. For decades, the following equation has been used to calculate absolute ages. The nice thing about uranium-235 and uranium-238 is that we have two long-lived radionuclides that both decay in isotopes of the same element, lead. And just by measuring an isotope ratio, you can determine an age here, if you know the decay constants. And if you know the uranium-235 to 238 ratio, right now, today, not when the solar system formed. That one you don't need to know, you just need to know the ratio today. And it was believed for a long time that this ratio is very well known, and this value has been used for a long, long time. But then, just 2 or 3 years ago, Prennecker et al. Found that there are variations in this 238 uranium to 235 uranium abundances, and that's pretty big variations from a cosmochemist point of view, because if you translate these variations into ages, and you need to correct your ages that you calculate if you find that the uranium isotopic ratio is different from what you expected, you find that this makes a difference in absolute ages of, here for these, there's a sequence of CAIs that are also shown here. So this makes up for age adjustments of up to 5 million years, which is, with the given precision today, a huge effect. One might ask where this deviation comes from. There are some ideas that it comes from the decay of curium-247, but this is still under debate. Taking this into account, it turned out that these CAIs, which I mentioned many times so far, that these CAIs are all formed in a very, very short time window. And we are now pretty proud that we are able to give the age of the solar system defined by the condensation of these CAIs with such a precision here, 4.56730 billion years with an error on plus minus 16 on the last 2 digits. It seems to be that most of these CAIs formed in a very, very short time window, maybe only like 20,000 years, which is nothing, as you know, compared to that age. However, there are still, with this new accuracy, with this new precision, there's now some problem with the aluminum-26 systematics. It seems to suggest that CAIs are processed over a little bit longer time scale. Also, what has been learned from these analyses is that chondrules also span a relatively short formation interval. It's only 3 million years, and it started right when also when the CAIs formed. So chondrule formation started directly when the CAIs formed, and then lasted for about 3 million years. But it's with chondrules, I have to say, it's still unclear how they formed. I don't want to go through all the theories that exist there. There are many theories, many models, at least as many as there are scientists who are spending their life on studying these objects. So there's not enough time to go through all of this. Some other system experienced some correction during the last couple of years. There was always the observation of the decay product of iron-60, and about 10 years ago, Tachibana and Haas came up with this extremely high value of iron-60 to iron-56 when the solar system formed. It was a big surprise, and there were some models coming up how to explain this. Need for some supernova trigger just when the solar system formed. There were recent results showing that there was a big flaw in this calculation here. It showed that what they've done 10 years ago overestimated the abundance of iron-60. New measurements with new techniques show that the value seems to be much lower, and so seems to be that there's no longer a supernova trigger needed for solar system formation. But with this precision comes now, as I already mentioned, some other problems. We observe a lot of heterogeneity, for example, also in aluminum-26. That was, as we believe, introduced into the solar system during the collapse of the proto-solar cloud. There's clear evidence for some heterogeneity at the time of CAI formation, which means that it can't be used so easily as a very high precision chronometer. This model it might come from winds of a massive stars, and so there are ideas how to explain this heterogeneity, and it would also decouple aluminum-26 and iron-60, but the details here are still being worked out. Same for beryllium, live beryllium-10 when the solar system formed, has been found in CRIs, but it's totally decoupled from other short-lived nuclide heterogeneity. And here it is believed that this is, has been explained as a record of variable irradiation conditions in the early solar system, which is in line with some astronomical observations of protostars. Again, let me come to some other major subjects. These are the pre-solar grains, or what I like to call real stardust, because these are stellar condensates that we find in primitive meteorites, for example. And they have been discovered about 25 years ago, the first pre-solar grains, but only 10 years ago, the first pre-solar silicate grains were discovered. This was only possible with modern technique, because in the old days to discover pre-solar grains, you basically had to burn down the haystack to find the needle. You had to dissolve the meteorite to look for what's remaining after this dissolving meteorite in hydrofluoric acid and things like that. And these were only very high temperature phases. These were diamond, this was silicon carbide, graphite, so things that are not easy to destroy, but we all expected there would be pre-solar silicates as well, and 10 years ago the first were found. Since then we have now more than 500 pre-solar silicates that had been found. Mostly show ferromagnesian composition somewhere between olivine and pyroxene. Some are crystalline, a lot of them seems to be amorphous or nanocrystalline material, as I said, with a composition between olivine and pyroxene. But there are also some weird samples have been found, even some pre-solar silica has recently been found. Where do they lie in the world of oxygen isotopes? It's again an oxygen isotope plot, but in the previous plot I showed you deviations in per mil, and now I'm plotting oxygen isotopes on a double logarithmic scale. This shows that we are talking about much bigger deviation, and this is why we are sure that these are pre-solar grains, because you can't do this with any process in the solar system. These are condensates that formed around evolved stars, and there have been assigned some groups here to the various pre-solar silicates and oxides that are also shown here. And you can see that these groups 1, 2, and 3 had been attributed to low mass RGB or AGB stars, different processes leading to slightly different isotope ratios, and there is this other distinct group, the group 4, that we think come from supernovae. A little bit about the abundances of these pre-solar samples. These are up to hundreds of ppm in primitive material. These are primitive meteorites, primitive carbonaceous chondrites, but even more primitive are the IDPs, the interplanetary dust particles that had been collected by NASA in the upper stratosphere. We have good reason to believe that a lot of them come from comets, and comets are believed to be very primitive, so it's not surprising that they also contain the highest abundance of several hundred ppm. This is the abundance in ppm. I think I never mentioned here here it's ppm. So 375 ppm in these IDPs, although single IDPs have been found that have even extremely high abundances up to 15,000 ppm. Coming from Stardust, the class of grains to Stardust, the mission, that was a mission that returned cometary dust in January 2006. By the way, they used the same switch to open the parachute, but this time it was put in the right way, so we had a nominal re-entry. It was here not necessary to catch it with a helicopter, but on its parachute it landed safely on the Utah desert, and here you can see the capsule. So the Stardust mission, first of all, it went to Comet Wild 2 to collect dust from there, but it also collected here interstellar particle stream. We know that there is a stream of interstellar particles entering our solar system, and on the way to the comet we had the opportunity to sample that dust as well, so it was basically 2 missions in one. So it visited Comet Wild 2, just a picture here, and it sampled the material, the dust grains with this collector here. So it consists of aerogel. It is basically silica with a very, very low density to decelerate the grains, and it forms these little holes here. And you'll see another picture just in a second showing how this looks like. So this thing here, a little bit bigger than a tennis racket, was used to collect the dust. And you see also here some aluminum foils that also were used as a sampling medium. And what we found there on these aluminum foils were little craters. And in these little craters you find material from the comet. And in these tracks, this is one of these little aerogel blocks about 3 centimeters long that taken out of its frame. And this might be able to see here a little track. Techniques had been developed to make little slices, and here you see a track a little over a millimeter long, and at the end of the track you have a little dust grain that you can analyze. So the first results, and you probably all heard about this, were a bit surprising. Wild 2 dust of this comet contains high temperature minerals. Here is shown a CAI that has been found, also chondrite-like components. And these are components where we are pretty sure that they must have formed close to the sun, not where the comet has formed way outside. On the other hand, there were no hydrous minerals, seems to be absent, so that water, for example, was never liquid, so the comet was never really very close to the sun for a substantial amount of time. And also other big surprise was that pre-solar grains were relatively rare, had a very low abundance. And this shows the first discovery of a pre-solar grain in Wild 2 material on the rim of one of the biggest craters found on this aluminum foil. And this little point here is showing its deviation and the oxygen 17 to 16 ratios again in per mil. And this has a 17 enrichment of a couple of hundred of per mil. If you think about the old plot here that we have seen before, puts it in this group 1. So that was the first pre-solar grain that has been found. But there was the expectation Wild 2 would be full of pre-solar grains. So from these first results, it picture formed that the grain formation took probably place close to the sun. Only way to explain these CAIs or other high temperature condensates. And then there must have been some particle transport to the outer region of the solar system where the comet formed, probably beyond the snow lines. And the picture appeared that comets seem to be less primitive than expected. But I should mention here already that there is some selection bias. This is showing one very complicated track. So the particle entered here. You have a terminal particle here. But a lot of material is deposited in this cavity, in this aerogel here. And well, most people first took the low-hanging fruit. It's much easier to extract such a particle here than all the extremely fine-grained stuff here. But this might be the primitive material, and this might be the exception, the high-temperature condensates that end up as terminal particles. From its bulk composition, it seems to be that Comet Wild 2 is pretty CAI-like, so basically the composition of the solar system. Some enrichments in some elements could be explained by some contamination. So but what you can also see here that the material is very heterogeneous. So individual samples are spanning several orders of magnitude, but the average is very close to CI or solar abundances. So WILT2 material is very heterogeneous. It's extremely fine-grained. It's heavily intermingled with aerogel. Shows CI-like bulk composition, contain high-temperature minerals, contains organics. I don't have the time here to talk about this. It seems to resemble the chondritic porous IDPs, those interplanetary dust particles that had been associated with comets. Up to now, a few more pre-solar grains have been found. Most of them seem to be coming from low-mass RGB or AGB stars. One grain might be coming from a supernova. But still, the abundance is very low. And I told you that IDPs have a very high abundance. And if you take what has been found so far, it's only 35 ppm, even less than in primitive meteorites. That was until recently a very surprising results. But there are now new results showing that these pre-solar grains lose their isotopic signature when they are captured. The material gets intermingled with isotopically normal material from the rest of the comet. Most of the comet is isotopically normal. And there were some tests made that proved that there is this destruction in the capture process. And from this, there are some correction factors that have to be applied. And in a recent paper by Christine Floss and co-workers, they showed that the true abundance of WILT2 is somewhere in this range. There are other groups saying it might be even higher, even up to 2,000 ppm. So the world is okay. We now know again we have proof that cometary material is very primitive, or at least it contains one of the very primitive building blocks of our solar system. I just want to briefly mention on this one slide that Stardust also collected contemporary interstellar dust. It's a real pain to get these particles out, or first to find these particles on the collector. While we have thousands of cometary particles, there are maybe only a dozen or so interstellar particles that had been found. And it took a huge effort involving actually more than 30,000 volunteers to find the tracks in the aerogel. They are very, very small. So far, 3 good candidates that we think that might be interstellar dust particles have been found, and we are close to now doing first isotopic analysis of these to show if they are really interstellar. But since they are so precious, we have been very careful, and so far no destructive technique was allowed for analysis. Just one slide, I want to mention the Hayabusa mission, because another mission that took place recently, or it returned in 2010, it sampled the S-type asteroid Itokawa. It's a Japanese mission. It returned tiny little grains from this asteroid and showed that this can be, or it's a perfect compositional fit with the LL chondrite, ordinary chondrite meteorite group. So it's a little bit boring because LL chondrites are not that interesting, but these are ideal samples to study what's going on asteroids, on the surface, in the regulars, ideal for studying space weathering, ion implantation, and these things, and this is done right now. This is all what I've showed you during the last half hour or so. Wouldn't have been possible with major developments in instrumentation. Or some substantial progress made over the last decade. The ways how to look at these samples. I just want to briefly mention a few techniques. Or, for example, for the Stardust mission, when Stardust was launched, there was no technique available actually to extract the grains out of the aerogel. These techniques had to be developed. They were very successful. Now they are routinely used, and you don't lose the particles by this, and we can analyze these little grains. Other techniques are the focused ion beam technique, for example, which allows you to, with nanometer precision, to make cuts on samples and making them available for other instruments like the nanosims that had been crucial, for example, for finding the pre-solar silicates in primitive meteorites with a lateral resolution, which is very important here, of down to 50 nanometers. On the other end, there is a MegaSims, an instrument basically built for almost the sole purpose to measure oxygen isotopes in the Genesis samples. Also a big success. There are techniques like high-resolution multi-collector ICP-MS, from which we got these incredibly high precision in isotopic analysis. And with this precision now, we have actually more problems because now nucleosynthetic anomalies have been found in almost all meteorites. So more to do until the next Protostars and Planets conference. TEM has seen some transmission electron microscopy, has seen some huge improvements. I don't have enough time to go into details here, but you basically now are able to look at individual atoms in these pre-solar diamonds. There's one technique now on the horizon that has been, first steps had been made to look at nanodiamonds that are only single-digit nanometers in size to get isotopic ratios of this. And I spent last 4 years or so of my life building a new mass spectrometer called Chile that will allow us to study small grains like stardust grain with even 1 order of magnitude better resolution than the nanosims, with an extremely high sensitivity, which means that every second atom in our sample we will be able to count. So we are reaching, in analytical techniques, we are reaching really a physical limit, and this instrument not only exists in an AutoCAD drawing. Here are some pictures recently taken in our lab, and we are very confident that this instrument will be operational before the end of the year. And this is my last slide. I think the last decade led to a wealth of new scientific discoveries from solar system samples, mostly due to the availability of exciting new samples from space missions, and due to the availability of new techniques that allowed studying these new as well as exciting samples with unprecedented resolution and sensitivity. Thank you very much.
Questions? Morby, go ahead.
Yeah, you made the point that aluminum was heterogeneously distributed at the beginning of the solar system, so it's not a valid chronometer. And Martin Bizzarro made the same point during questions a couple of days ago.
Okay.
Nevertheless, the new results on chondrule ages from lead-lead dating do not differ that much from those inferred from aluminum-magnesium systems. So now the chondrules range from time 0 to 3 million years, and before it was from 500,000 years to 3.5 million years. So can you quantify a little bit which kind of error the previous analysis based on aluminum-magnesium chronometer could have? Which level of confidence can we still look at papers like, Villeneuve et al., for instance, in Science, or should we dismiss them completely? No,
not at all. I think the problem here is that our accuracy or our precision of measuring these things has improved so much that we now see that there are these variations. It doesn't mean that all the old papers are not valid, and especially the Villeneuve paper that gives some explanations on these heterogeneities. It seems to be only a very small group of samples that show this heterogeneity. So for a lot of samples, it still seems to be a valid chronometer. But I just want to caution you that you have to be a little bit more critical and think, is this well established here? Like we thought for decades in the case of uranium-lead dating, that we knew the uranium isotopic ratio, and then it turns out it's not. It's not stable, and so it's an ongoing field, and I hope for the next conference we have more insights and maybe final word on this.
Go ahead.
directly, Caltech. You mentioned the D2H isotopic ratio in cometary water, and you said that it was higher than the Earth-ocean value, and that precludes comets as a possible source of Earth water. I would like to point out that there are new Herschel measurements in comets coming from Kuiper belt as opposed to the Oort cloud that are low and consistent with VSMO. I won't make any statements of what the implications may be about the origin of ocean water, but what the Herschel data show clearly is that there is a diversity in the D2H isotopic ratio in comets, and this canonical value of 3 × 10⁻⁴ can no longer be defended.
Yeah, thanks.
Please, go ahead.
Hi, Ruud Visser, University of Michigan. You mentioned beryllium-10 heterogeneity in CAIs and linked that to variable accretion in the solar nebula. Can you explain it a little bit more? Because I didn't understand quite how that was connected.
Unfortunately, I have to admit, I got this slide from one of my co-authors just a couple of days ago. Just let me switch back to that slide. Oh, it's... sorry about that. Oh,
you skipped past it.
Yeah, I passed it. Okay. So what my co-author told me here is that there is this strong heterogeneity that has been found in CAIs, and the interesting thing is that it is kind of decoupled from other heterogeneities of other short-lived nuclides. So I'm not sure if I'm answering your question correctly, but it seems to be that you need an extra way to make this heterogeneity, and what I was assured is that this could be explained by, you have to make somehow this beryllium-10, which is not so easy. It's not usually not formed in stars so easily, so it's usually made by irradiation. And if you have some variable irradiation conditions in the early solar system, which has been observed for other protostars, then you can explain this variability in beryllium-10. So this is how I understand the story.
Okay, thank you.
Question up there?
Yeah, I have a curiosity about the Stardust mission, because the system for collecting the dust particles seems pretty, how can I say, challenging, since the relative speed between the collector and the particle is highly supersonic, and the kind of impact shock that the dust grain encounter when enter the aerogel, I've read in a study that has been done with steel, austenitic steel spheres, create a pretty strong metamorphism due to the impact itself. And my concern is about the kind of alteration that can have produced in the dust particles, and which kind of bias it can have introduced to the consideration about the mineralogy itself, and for example, the hydratation of the silicates.
Okay, yeah, there has been a long discussion about this. On the other hand, there has been experience in the lab with dust accelerators. The relative speed in case of Stardust was about 6.1 kilometers per second. And these experiments in the lab seem to indicate that you still would see some signature of phyllosilicates. If you have hydrated minerals, for example, you would still see that signatures. Of course, you have some alteration. This is a big concern. But by doing this calibration experiments in the lab with kind of comparable materials, we think we know what's going on. And of course, there's still a debate, but I would say we have no clear proof that there were any hydrated minerals in Bilge 2.
Please go ahead.
Wes Fraser, Herzberg Institute for Astrophysics. This question might be a result of my inability to keep up with the Stardust results, but has anyone looked at the relative age of the CAI discovered in that mission compared to the distribution of meteoritic CAIs? Because it seems to me one might be able to provide at least moderate constraint on the mixing timescales that brought that CAI out from the hot region. Has anyone speculated on that?
The problem here is, although there have been CAI-like material been found or CAI has been found, they are way, way smaller than what we see in meteorites. So it is really, so far, there were some measurements of aluminum-26 or so, but they are not very clear, and I think we need the new techniques like the Chile instrument I'm working on, and that will hopefully be finished later this year, to look at these grains. We also hope with this technique be able to do exciting stuff like absolute dating of pre-solar grains or things like this, but the analytical techniques so far were just not good enough to give us a lot of results, and from one CAI of Stardust you cannot infer that much. There's a little bit of data, yeah.
Very good. 2 last questions, one here, one there. Go ahead.
Hi, Nicole Cabrera, GSU and EPAG. So I have a question going back to what potentially brought water to the Earth. And so I see that there's this, you mentioned that there's a lower D to H ratio for these primitive meteorites.
Yeah.
So there's still a discrepancy. And so I'm assuming that this discrepancy is easier to explain than the higher discrepancy. Can you explain how
yeah, it's easier to push basically the D to H ratio up if you bring water to the Earth, and you might think that some of the hydrogen later on gets lost or so. Whatever of physical process you have on Earth, that would always make it easier to lose hydrogen compared to deuterium. So you go to a higher D to H ratio from whatever you start with. It would be very difficult to deplete deuterium or to enrich only hydrogen. And so going up in that plot is kind of easy, but going down is kind of impossible. So going down from the values of the comets seems to be implausible, but going up from the slightly lower values of the primitive meteorites seems to be much easier.
Thank you.
Last question, please.
Amaury Chiabo from the University of Bern. I have a question regarding the Stardust mission, because there has been some problem of contamination of the aerogel. So how much confidence should we put in the results provided by this mission?
I think a lot of confidence. The problem is always what results. The problem is, and I didn't mention those results or didn't go into any details, for example, about organics. We know that the aerogel is contaminated with terrestrial organics. So, and these are all altered a lot during impact, much more than solid minerals. And so I would say one has to be careful, but so far all the publications on this were very careful about organics in World 2. We know that there are seem to be good evidence for some classes of organics like PAHs or so. There is some concern about some volatile elements. There will probably never be good numbers on elements like oxygen, because aerogel consists mainly of SiO2, so there's a lot of oxygen there. So abundances of volatile elements is all questionable, and actually, to my knowledge, there haven't been any real numbers published there. For major rock-forming elements, for example, I think the numbers are pretty solid. There are some exceptions with some weird elements, but these are usually very volatile. So most of the results, I think, are pretty solid.
Very good. Let's thank our speaker again, but don't go anywhere.